Okay, next our speaker is Kazaros Kazarian. His talk is weighted HP spaces with admissible weights. Please.
Thank you. First of all, I would like to thank organizers, especially Alexei Karapetyan, for this invitation. Also reading the article about Professor Samko, I discovered that we have something common, that both of us will find some help by Professor Lysorkin and academician Nikolsky. Both of them I am very grateful. So I would like to say some words on the whiteboard. Yes, in order to explain the question how it arises. I am speaking about HP spaces with weights, but the problem comes from the famous theorem of Seguiot. Yes, I would like write them 2 minutes. I would like to use the method of Alexei Karapetyan's. So the Seguiot theorem I can interpret in the following way: that linear span or closed or linear span in LP W of the system coincides with LP W if and only if integral on T logarithm omega T dt is equal to minus. Okay. So many years ago I observed that if this condition is not true, then the system will be minimum. Yeah? If I write it somewhere in one of papers without a roof, and it was my bet to come to this question, because I would like to describe if it is possible the bi-orthogonal system of the system of analytic monomials, yeah, trigonometrical monomials. This was my
Space or H space.
LP.
From 0 to infinity or from minus infinity?
No, from 0 to infinity. What is? No, it's famous theorem. It's not my theorem. Okay. Now, so let's go ahead. But I have to. Okay. It's well known that any function from HP. Now I am distinguishing HP on the unit ball and HP on the boundary. Okay. So if a function belongs to HP on the unit ball, it can be factorized in the following way. Okay, these functions are called respectively inner and outer function. The name was given by Berling in his famous paper. Okay, and moreover, the outer function can be written in the following way. And there is no unicity, but it's not so important. Okay, first of all, I would like to investigate, having in mind Segios theorem, okay, on the boundary of the unit ball, say on T. Yeah? So I said, I think that there is a definition. Yeah. So if the weight function is admissible, which means that integral of logarithm of the weight is not equal to minus infinity, or the logarithm of the weight is integrable, okay, then I call it admissible function. And what I'm going to prove that not only it's minimal. Minimal, it means that there is a bi-orthogonal system in its conjugate space. Or in this case, you can say that there is a bi-orthogonal system in the space LP prime. Okay. So in order to have unicity, we consider the closed span of these functions. Okay. And so if we have the conjugate space of HP, which we consider can be HP prime, so there, sorry, I have to say about weighted functions, weighted spaces. Okay. No, this only I have given some notation. Okay. So now I would like to speak some words about weights. Okay, we have all these conditions about weights. Here is the definition of admissible weight function. Of course, we should speak about AP classes of weight functions, which sometimes is called Makenau's condition. And here I would like to consider another class of weight functions, which is not so popular, or is much less popular. As you see, this class of functions appeared in Marvin Rosenblum paper. Okay, coordinates I've written here. And it seems, say, complicated condition. Okay, but you can observe not yet, you cannot observe now nothing, but I can say beforehand that all classes of Makenau weights enter into this class of functions, which I call Rosenblum class of weight functions. Okay. Now, what Rosenblum proves in his paper, which I have cited, which is, I consider is a very important paper, but it's not so famous as Makenau's paper. Okay. One of the conditions, terms that he has proved is the following theorem, which I formulated here. Also, I would like to mention that Makenau's conditions in another form appeared in this paper also. Okay. So, but probably Makenau's paper was so popular because he finds necessary sufficient conditions for boundedness of maximal function, first of all, and always because in his proof it appears interpolation. So there is many technical moments that help to obtain other results. Okay, so here I am. Here we have the definition of weighted HP space for admissible weight function. Okay. So we call HP W, but H here is not calligraphic. Okay. And here I distinguish HP space with weight on the unit circle, sorry. Okay. It comes out that in classical case we have that these spaces are isomorph, but for weights it's not so. Okay, then this is one of the results which I'm going to announce here. So, first result is the following, that the system e to the power IGT, from 0 to infinity, is m basis in HP with the weight W. Okay, so what means m basis? It means that the system is closed. It's obvious because it's closure denoted by HP omega. So it's minimal. Okay, it means that it has unique bi-orthogonal system. And moreover, this bi-orthogonal system is, we can say, complete with respect to HP omega, or we can say that it's closed in the conjugate space or dual space. I skip the description of dual space of HP W because it's a little bit complicated. It's long a little bit to describe it, okay? But I have the description of the dual space and representation of functionals from this space. So we go ahead. The next theorem is that the system which we are considering is uniformly minimal in HP W if and only if this condition holds. What means uniformly minimal? It means that the product of a norm of any element of the system with the norm of element with the same index in the conjugate, in the dual space, okay, this product is uniformly bounded. So these systems are called uniformly minimal. For instance, if you have to decompose an element of the space, okay, evidently this is a necessary condition if you would like to have convergence. Okay, so this is only an important thing to have in mind when you are studying a complete minimal system or decompositions of elements with respect to this system in a given space. Okay, so these conditions also I have not formulated will give us that the following theorem, that if P is greater than 1, okay, and less than infinity, then necessary and sufficient conditions in order that the system is Schauder basis in the space HP omega is that the weight should be AP weight. I don't write this because it can be obtained also in another way, okay? Of course, solo the condition of sufficiency. And Schauder basis, it means that the system is complete minimal or is an M basis, and all decompositions converge to the corresponding element of the space. Okay. Here we have one of the main theorems which I have proved. is the following, that the system also is an A basis in the space HPW, if and only if the weight belongs to the Rosenblum's class. Okay, here I write this relation in order to know that any weight functions which belong to any AP class enters in the class of Rosenblum. And what it means A basis, it means that if we decompose any element of the space, HPW, and afterwards consider the summation method, Abel summation method, okay, then any element can be represented as the Abel sum of the decomposition. I'm going too fast. Okay, so here is something a little bit delicate that I was thinking how to say smoothly, okay? So Rosenblum in his article, which I admire, okay, in the introduction formulated the following statement, okay, that if a weight function belongs to the class R, okay, then there is an operator, lambda, which is called, such that any element which belongs to, here I have not changed the notation. So in my notation, it should be HP calligraphic omega on 2 HP omega. Then that such operator lambda and its inverse operator are bounded. But he don't formulate a theorem. At the end of the article, he gives some scheme of some details around the proof of this statement, but I think that it's not complete, okay? But this gap can be filled. I consider that it is Rosenblum's theorem, okay? And so here I write the kernel when you consider the composition of an element with respect to the system which we are considering, okay? And afterwards you consider the Abel summation method, okay? So first of all, we have that the function f r e I t, okay, defined in this form, it's holomorphic, okay, and non-tangential limits represent the function given on the boundary. And this is true for any admissible. So here you don't need to have that the weight function belongs to the Rosenblum class. Okay, any admissible weight function, you have this representation. Here the convergence is non-tangential almost everywhere. Okay, and this will give the operator lambda that speaks Rosenblum, okay, in a precise form. Okay. And we have also the following theorem, that if omega belongs to the Rosenblum class, okay, and F belongs to the class HP on the boundary, then the holomorphic function belongs to calligraphic HP omega or W. Okay? So, and it is true also that necessary and sufficient conditions that these spaces, HP calligraphic and HP on the boundary, they are isomorph if and only if the weight function belongs to L. This is some strengthening of the Rosenblum's theorem. Okay, so I am ending a little bit earlier, but it's good. Okay.